We are going to start with transformer today. The transformer. A transformer is an electrical. A transformer is an electrical device. Is an electrical device for converting an AC at low voltage into that at high voltage or vice versa. If we want to convert an alternating current from low voltage to high voltage or from high voltage to low voltage, a transformer is required. If it increases the input voltage, it is called step-up transformer. If it increases the input voltage, it is called step-up transformer. And if it decreases the input voltage, it is called step-down transformer. It is called step-down transformer. Now, transformers, I am drawing the diagram of this transformer. Just look. It is like this. So it is constructed like this. A transformer is like this. We have this hollow rectangular sheets, one over the other. We stack them, and one over the other we stack them, and this is called a transformer. This is the shape of a transformer. And now I am going to show you two types of transformers. One is called step-up transformer, the transformer in which the input voltage is very low and output voltage is high is called step-up transformer. A transformer which is used to increase the output voltage is called step-up transformer, and the transformer which is used to decrease the output voltage is called step-down transformer. So based on this concept, there are two types of transformers: step-up transformer and step-down transformer. So we have here like this. This is the symbol of an AC source. This is the symbol of an AC source, AC voltage, AC source. And look how much turns how much turns of wire we have here. 1, 2, 3, and 4. So we are having 4 turns of the wire here, and now this is called P, and this is to load. If we are connecting a transformer to a load, so look how many turns of wire we have here: 1, 2, 3, 4, 5, 6, 7 turns, and here we have 4 turns. So this one is called the wires which are connected to the input supply, the wire which is connected to the voltage source, that that portion of the transformer is called primary, and the wires which are connected to the load, that portion of the transformer is called secondary. So I have marked P for primary and S is for secondary. So this is a transformer. Basically, this transformer is used to increase the output voltage because the number of turns in the secondary winding is more than the number of turns in the primary winding. So when we increase the number of turns in the output, then output voltage increases. And when we decrease the number of turns in the output, then the output voltage decreases. Is this clear to you? Is this clear to you?
Yes.
Okay. Now next, the principle of its working. It works on the principle of mutual induction, that is, when a changing current is passed through one of the two inductively coupled coils, an induced EMF is set in the other coil. It works on the principle of mutual inductance. Actually, this coil and this coil, they are not connected to each other directly. So it works on the principle of mutual induction when an EMF is when a flux associated with this primary coil changes, then it induces an EMF in the secondary coil. So this is the principle. This is the principle which works here in the case of transformer. So this principle is called principle of mutual induction. Now construction. Construction is a transformer essentially consists of two coils, insulated copper wire, two coils of insulated copper wire having different number of turns and wound on the same and wound on the same soft iron core. The coil P to which electric energy is supplied is called the primary, and the coil from which energy is drawn or output is obtained is called the secondary. So the coil from which the input voltage is derived is called primary, and the coil which is connected to the load is called secondary. Two types of arrangements are generally used for winding of primary and secondary coils in a transformer. First is core type. There are two types of transformer. For winding primary coils, for winding primary and secondary in a transformer, two types of arrangements are used. First is core type. Two types of arrangements are used. First is core type. Core type. In the core type transformer, the primary and secondary coils are wound on the separate limbs of the core so that the core is largely surrounded by the coils. Many of the modern transformers are of closed core type as shown in figure A. So many of the modern transformers are of this type only. So I'm not drawing the diagram again because it is drawn in the notes. So this is core type. So core type is just similar to this, and the second one is shell type. Second one is shell type. In the shell type transformer, the primary and secondary coils are wound one over another on the same limb of iron core. The coils are very largely surrounded by the iron core as shown in figure B. So look, what is shell type transformer? The construction of shell type transformer is like this. This is primary, and this is secondary. So in the shell type transformer, both primary coil and secondary coil, they both are bound on the same limb. So the construction is different, but the principle of working is the same. They work on the principle of mutual induction. Working now, we are on the last line of page number 33 of your notes. Working, as the alternating current flows through the primary, it generates as the alternating current as the alternating current flows through the primary, it generates an alternating magnetic flux in the core, which also passes through the secondary. Which also passes through the secondary. As alternating current flows through the primary, it also generates an alternating magnetic flux in the core, which also passes through the secondary. This changing flux sets up an induced EMF in the secondary and also a self-induced EMF in the primary. If there is no leakage of magnetic flux, then flux linked with each turn of the primary will be equal to that linked with each turn of the secondary. If there is no leakage of flux, then flux linked with each turn of the primary is equal to the flux linked with each turn of the secondary. Now, theory. Consider the situation when no load is connected to the secondary, that is, its terminals are open. Let N1 and N2 be the number of turns in the primary and secondary respectively. So, if N1 and N2 be the number of turns, if N1 and N2 be the number of turns in the primary and secondary respectively, then induced EMF in the primary coil, theory of transformer. Induced EMF in the primary coil E1 is equal to minus N1 d phi by dt. This is the formula of induced EMF. And induced EMF in the secondary coil minus N2 d phi by dt, where phi is the magnetic flux linked with each turn of the primary or secondary at any instant. Thus, E2 upon E1 is equal to, what is E2? Minus N2 d phi by dt upon minus N1 d phi by dt. d phi by dt will get cancelled by d phi by dt, and minus sign will get cancelled out by this minus sign. E2 upon E1 is equal to N2 upon N1. E2 upon E1 is equal to N2 upon N1. So the concept of working when the question related to transformer is asked in the exam, then they asked basically how a transformer works. So you have to write about the working, and it is also a theoretical question will be made on this topic. So you have to explain the working, and you have to explain the theory, and in the when you have to construct it, then you have to construct both type of transformers. This is core type and this is shell type. So you have to draw both type of transformers. And after that, the theory is very much simple, that induced EMF in the primary coil induced EMF is minus N1 d phi by dt. Why the flux is same? Because the basic structure is same. Because the basic structure is same, so what flux will be associated with this? The same flux will be associated with secondary. That's why we are taking d phi by dt as we are taking it as d phi by dt, not d phi 1 by dt here and d phi 2 by dt here. No, we will take it same because the same flux will be induced in both primary and secondary. So E1 means induced EMF in the primary coil, it will be minus N1 d phi by dt, and induced EMF in the secondary coil E2 is equal to minus N2 d phi by dt. And if we divide it both, this one is for secondary, means output EMF, and this one is for primary means input EMF. So E2 divided by E1 will be equal to N2 divided by N1. It means that if we have the ratio of this number of turns in the primary and secondary, then we can simply calculate this E2 upon E1. So this is basic theory and working. So this much you have to explain in exam if they ask about it. Let E be the EMF applied. Now I am again going to page number 34 of the notes, last 4 lines. Let E are the notes handy with you, na? Notes are handy with you? Yeah. Okay. Okay. Now, let E be the EMF applied to the primary. By Lenz's law, self-induced EMF E1 opposes E in the primary coil. Resultant EMF in the primary. Let E be the EMF applied to the primary. So if the EMF applied to the primary means the EMF of the voltage source, if it is E, then resultant EMF in the primary is E is the EMF applied to the primary, then resultant EMF in the primary is equal to E minus E1. E minus E1. This EMF sends current I1 through the primary. Sends current I1. This EMF sends current I1 through the primary. Therefore, E minus E1 is equal to I1 into R. But R in bracket write resistance of primary is very small. So I1 into R can be neglected. I1 into R can be neglected. So E minus E1, E minus E1, I1 into R can be neglected. Neglected means 0. So this will become 0. E minus I1 is equal to 0 means E is equal to E1. That is E minus E1 is equal to 0. It implies that E is equal to E1. It implies that E is equal to E1. It means that applied EMF is exactly equal to the EMF developed across the primary. Uh, Thus, E1 may be regarded as the input EMF. Therefore, E1 may be regarded as the input EMF, and E2 may be regarded as the output EMF. Regarded as the output EMF. E2 upon E1 is equal to N2 upon N1. N2 upon N1 is called turns ratio or transformation ratio of the turns ratio or transformation ratio of the transformer. Now, in a step-up transformer, N2 is greater than N1. It implies that N2 upon N1, if I bring this N1 in the denominator of N2, then N2 upon N1 will be greater than 1. And what N2 upon N1 is equal to? N2 upon N1 is equal to E2 upon E1. Therefore, E2 upon E1 is greater than 1, and if I take E1 here, then E2 is greater than E1. E2 is greater than E1. So this was the case of step-up transformer. In a step-down transformer, N2 is less than N1. N2 is less than N1. So it implies that N2 upon N1 is less than 1, and it implies that we know that N2 upon N1 is equal to E2 upon E1. E2 upon E1 is less than 1, and if I take this E1 here, then we will get E2 is less than E1. It means that output voltage is less than the input voltage in case of step-down transformer. Next, currents in primary and secondary. currents in primary and secondary, assuming if the transformer is an ideal transformer. In case of ideal transformer, there are no power losses. It means that input power will be exactly equal to the output power. So if the transformer is an ideal transformer, then input power will be exactly equal to output power. If the transformer is an ideal one, then input power is equal to output power. What is input power? We know that power is equal to voltage into current. So input power is E1 into I1 and output power is E2 into I2. If I bring this E1 here and I2 here, and I1 upon I2 is equal to E2 upon E1. I1 upon I2 is equal to E2 upon E1. This is equation 1, and this is equation 2. Combining equation 1 and 2, we get E2 upon E1 is equal to N2 upon N1 is equal to I1 upon I2. Have you noted down till here? Have you noted down till here?
Still writing, so 1 second.
Okay, just give me 2 minutes. You write it. I am coming back in 2 minutes.
Okay, sir.
So now, let's move on to the next slide. Energy losses in efficiency of a transformer. Efficiency of a transformer is defined as eta is equal to power output upon power input upon power input into 100, and it will come out to be in percentage. Now energy losses in transformers. So energy losses in transformers, copper loss. Some energy loss is due to heating of copper wires used in the windings. This can be minimized by using thick copper wires of low resistances. If we use thick copper wire of low resistances, then copper losses can be reduced. Second is eddy current loss. So eddy current loss, actually eddy currents are not in slavers. So some current actually, in the case of mutual induction and self induction, some current leaks from the circuit. So that type of current is called eddy current. So you simply learn it that eddy current loss is also an important loss in case of this transformer. So we have to make some arrangements to reduce eddy current losses. The alternating magnetic flux induces eddy currents in the iron core, which leads to some energy loss in the form of heat. This loss can be reduced by using laminated iron core. So, laminated iron core, if we use the iron core, if we laminate it, then this type of losses can be reduced. Hysteresis loss. AC carries iron core through cycles of magnetization and demagnetization. So, alternating current first increases and then decreases. It is not a constant current, it is alternating current. So alternating current, first of all, it magnetizes the core of the transformer, and when alternating current decreases, alternating current has such type of cycle, na? Firstly it increases, then first it goes in this direction, then it goes in this direction. So when it goes in this direction, it magnetizes the core of the transformer, and when it goes in this direction, it demagnetizes it, means it removes the magnetism. So this alternate cycles of magnetization and demagnetization, so they in such type, in because of this magnetization and demagnetization, a loop is formed. If we draw a graph between current and magnetization, then such type of graph is formed. We have done this, I think you remember that we have done this in chapter number 5, hysteresis. So hysteresis loss is called when it magnetizes the transformer, then a humming sound comes from the transformer. When it demagnetizes, another type of humming sound comes from the transformer. So this humming sound, actually this sound is also a form of energy, and this sound goes out of the transformer. So this also creates a little bit loss from the transformer. AC carries iron core. I'm reading it out from the notes. AC carries the iron core through cycles of magnetization and demagnetization. Work is done in each of these cycles and is lost as heat. This is called hysteresis loss, and it can be minimized by using core material having narrow hysteresis loop. We have to use a core material which have a narrow hysteresis loop. So in that case, hysteresis can be reduced. Now, flux leakage. The magnetic flux produced by the primary may not fully pass through the secondary. Some of the flux may leak into air. This loss can be minimized by winding the primary and secondary coils over one another. If we wind primary coil and secondary coil over one another, then magnetic flux leakage loss will be minimized. Fifth type of loss is humming loss. As the transformer works, its core lengthens and shortens. When the transformer works, its core, this is called the core of the transformer. This one is called core of the transformer. It lengthens although its length increases by a very small amount, it lengthens and it shortens, lengthens, shortens, lengthens, shortens. As the transformer works, its core lengthens and shortens during each cycle of alternating voltage due to a phenomena called magnetostriction. This gives rise to a humming sound, so some of the electrical energy is lost in the form of humming sound. So when the iron core lengthens and shortens during each cycle of magnetization in transformer, then some humming sound occurs, and this type of sound called humming loss. Now, uses of transformers. First uses, small transformers are used in radio receivers, telephones, loudspeakers, etc. Second, in voltage regulators for TV, refrigerators, air conditioners, etc. Third, in stabilized power supplies. Fourth, a step down transformer is used for obtaining large current for electric welding. Fifth, a step up transformer is used for the production of X-rays. So these are the uses. You can learn any 2 or 3 uses of the transformers. So any type of question they can ask about in transformer, they can ask about their uses, their losses incurred in transformer, or the construction of the transformer theory and working. So you have to learn everything. At least you have to learn all these things, all those things which I have written over here. Okay, Anusha, is this clear till now?
Yes.
Okay. Now, question 1. Let's do some numericals also of these transformers. Question 1. The primary coil of an ideal step-up transformer has 100 turns, and the transformation ratio is also 100. The primary coil of an ideal step-up transformer has 100 turns. Primary coil, the number of turns in the primary coil is called N1. N1 is equal to 100. N1 is equal to 100. And the transformation ratio is also 100. What is transformation ratio? N2 upon N1. N2 upon N1. It is also 100. N1 is also 100 and N2 upon N1 is also 100. Now, the input voltage and the power are 220 volt and 1100 watt respectively. Input voltage is E1. We have proved it in transformer that E1 is regarded as the input voltage. E1 is equal to 220 volt and input power P1 is equal to 1100 watt. Calculate first part, number of turns in the secondary. In first part they are asking that number of turns in the secondary. N2 upon N1 is equal to 100. It implies that N2 is equal to 100 multiplied by N1. N2 is equal to 100 multiplied by 100, 10,000. The number of turns in the secondary is 10,000. Now, in second part they are asking current in the primary. Current in the primary means I1. We know that E2 upon E1 is equal to N2 upon N1 is equal to I1 upon I2 is equal to I1 upon I2. Okay, but we don't have I2. We have power, we have input power P1. So P1 is equal to E1 into I1 and it is equal to 1100 watt. And what is E1? E1 is 220 into I1 is equal to 1100. 0 will cancel out the 0. 22 5s are 110. I1 is equal to 5 ampere. Is that clear? Is that clear? Tell me.
Yes.
Okay. Third part, voltage across the secondary. Voltage across the secondary means they are asking about E2. E2 upon E1 is equal to N2 upon N1. And this N2 upon N1 is transformation ratio. This is given as 100. So E2 is equal to E1 multiplied by N2 upon N1. So what is E1? E1 is 220 and N2 upon N1 is 100. So 22000 volts. This one is E2, 22,000 volts. Now fourth part, current in the secondary. Current in the secondary means they are asking about I2. So since E2 upon E1 is equal to N2 upon N1 is equal to I1 upon I2, not I2 upon I1, I1 upon I2. So N2 upon N1 is 100. I1, what is this I1? 5 ampere. And upon I2, let us bring I2 here and 100 here. 0.05 ampere. Current in the secondary is 0.05 ampere. And fifth, power in the secondary. Power in the secondary. Power in the secondary P2 is equal to E2 into I2. E2 is 22,000. Decimal will go away and 100 will come in the denominator. 22 5s are 110 and 1 0 is there. 1100 watt. Or we can also say that since it is an ideal transformer is that type of transformer in which no losses are given. So no losses are given, that's why the input power will be equal to the output power. Input power was given as 1100 watt, so output power is also 1100 watt. You can calculate it or simply you can write it. It is an ideal transformer in that input and output powers are equal. All right, now just check question number 2. How much current is drawn by the primary of a transformer which steps down Next question. how much current is drawn by the primary of a transformer? By the how much current is drawn by the primary of a transformer? It means they are asking about I1. Which steps down 220 volt to 22 volt. Which steps down, it means E1 is 220 volt, steps down means output voltage is less than the input voltage, 22 volt. To operate a device with an impedance of 220 ohm, to operate a device with an impedance of 220 ohm. To operate a device with an impedance of 220 ohm, it means that when we want to operate a device, that device is connected in the output of any transformer. Device is always connected to the output of any transformer. So what it is given, Z means resistance, impedance means resistance of the output is given. Therefore, a device is always connected to the output of a transformer. So E2 is equal to I2 into Z. E2 is 222, I2 we don't know, and Z is 220. 22 tens are. So I2 is equal to 1 upon 10, means 0.1 ampere. This one is I2. Since I1 upon I2 is equal to E2 upon E1, I1 is equal to I2 into E2 upon E1. I1 is equal to, what is I2? It's 0.1, E2 upon E1, 22 upon 220. Decimal is gone. 22 tens are 0.01 ampere. Is that clear to you?
Yes.
Okay. So the last topic of this chapter is AC generator, and you might have read this chapter in magnetism and matter in chapter number 5. So this is the same. No, sorry, electromagnetic induction. You might have read this in electromagnetic induction. So no problem. It will take only half class, not full class. So tomorrow I will complete this AC generator, and after this chapter, which chapter do you want to start?
My physics exam is next Sunday, I mean Monday.
Mhm.
What chapter can you complete by then?
Which all chapters are coming in that exam?
The entire portion, sir.
Which one?
The entire portions, full 2 books.
Oh, full 2 books. Okay, okay.
So, which of like the remaining chapters after AC can you do within the time from next to next week? Like this week and next week, you have till Monday, next to next week.
Okay,
Monday or next week.
okay, okay, okay. Oh, in the first book we have done that chapter 1, only chapter 1, chapter 1, 6, 7. Anna, can you tell me which all chapters we have completed till now? I think chapter 2 and 3 are left.
We completed the first one. We completed magnetism and matter, magnetic effects. What do you call it? EMI. We
Huh?
finished
Hmm.
EMI. We finished AC now.
Hmm.
Yeah.
I think we have completed a half chapter, a second chapter also, na? A little bit. I think 50% we have completed
A
it.
little portion of it. Yeah.
Okay, okay. We can do that. We can do that. We can do chapter number 2 because chapter 1, 2, and 3 are interrelated.
Chapter number 2 is still big. Wait. Can you do like dual nature, small atoms, nuclei, all of these are small chapters.
Anuja, actually, these chapters, if you say, I can do that also, but these chapters are really very small chapters and very easy also. Very easy also. These chapters you can also do on your own also. And if you say I will do that, but I'm worried about these three chapters: chapter 2, chapter 3, and the ray optics. These three chapters are really very big chapters.
But then they're also really big, so like anyways we have like less than like 2 weeks. So like how are we gonna do it? And I have other exams also.
Okay.
Classes will be cancelled.
Okay. Okay, then we will do the last four chapters. Dual nature of radiation and matter, we will start it tomorrow. Dual nature of radiation and matter, then atoms, then nuclei, and then
Is EM wave like big or something?
EM wave is very small chapter. We will do that. We will do that also. You know that. Okay, the idea is very much clear to me now.
I've done dual nature of radiation matter. It's very small, I did it.
Oh,
The other
that's
chapter.
atoms, nuclei. You want to do, na?
Yeah.
Atoms, nuclei, electromagnetic waves, semiconductor devices. We will do these chapters. We will go for this. Okay. And after this exam, then we will do the remaining chapters.
And this week, like up until Friday, I need to take like many classes. I cannot take longer classes because like these next 2 3 days are all I can spare. And then again from Monday evening
Hmm.
to like hold on Wednesday, Monday evening, Monday, Tuesday, Wednesday.
Hmm.
These 3 days you have. Then again